Hello everybody. Today's lesson is on geometric probability. Your learning target is to use geometric models to solve certain types of probability problems. Okay, we're all familiar with probability. Something like what's the probability that if you toss a coin you'll get a heads? Okay, we're going to look at that in a second. But what exactly is probability? Fill in our blanks here. Probability of an event, and we call it P. Probability of an event P is the likelihood that the event will occur. When the possible outcomes are equally likely, the theoretic probability of an event is the ratio of the number of favorable outcomes to the number of possible outcomes. So when you're looking for probability, you always want to divide the number of possible outcomes into the number of favorable outcomes. So back to our coin problem, if we're going to toss a fair coin, and by fair it just means it's not weighted. Sometimes you might run into someone doing magic and they have a coin that's not exactly fair. In other words, it always lands one way or another. But we're going to take just a coin out of our pocket and we're going to flip it up, and we want to know what the probability is that we're going to get a heads. Well, the probability for heads is going to be the number of favorable outcomes. What is the number of favorable outcomes? 1, of course. So one favorable outcome, heads, and it's divided by the total number of possible outcomes. Well, what's the number of possible outcomes? 2, right? I could get a heads or tails. So 2. So when I toss a coin one time, the probability that it'll land on heads is 1/2. And I can express this as a percentage. Of course, that would be 50%. I got a 50-50 chance of getting heads, so of course I got a 50-50 chance of getting tails also. All right, how about another one? Suppose we got a standard deck of cards and we want to know what the probability is that we'll pick a face card. Well, we got to know what a face card is. We're talking about a jack, a queen, or a king. All right, so if we have, now we got to know how many suits do we have in a standard deck of cards. So we have 4 suits. 4 suits. What do we got? We got spades, we got clubs, we got hearts, and we got diamonds. Right? So we got 4 suits. We got 52 cards. 52 cards in the deck. So each suit has 13 cards. So 13 cards per suit. All right, so that's how we get our 52. So if each suit has a jack, a queen, or a king that has all those cards in it, so I got 4 suits, 3 face cards per suit, then I got a total of 12 face cards, right? Got a total of 12 face cards. Okay, so that would be my favorable outcome, right? I got 12. If I randomly have this deck of cards spread out and I randomly pick a card, there are 12 favorable outcomes because there are 12 face cards. So probability, we'll put for a face card here, is the number of favorable outcomes. We know that's 12. And divided by the number of possible outcomes, well, that's how many cards are in the deck. 52. So our probability is 12/52, and of course we want to simplify this. So let's see, what's the largest number that'll go into 12 and 52? Does 4 go into 52? I believe it does. 4, 12, so 13. So yep, I'm going to come over here and write this. When I simplify 12/52, I get 3/13. So there's our probability. You know what? I'll take that back. Let me put it over here on the side. So the probability for a face card is 3/13. All right. So that's what probability is. Okay, in geometric probability, points on a segment or in a region of a plane represent outcomes. Okay, so let's start with probability and length. I got this segment here, AD, and it says point S on AD is chosen at random. So I'm just going to come in here somewhere and I'm going to randomly pick a point. I don't know where because it's going to be at random. I'm going to have my eyes closed, I guess. And so we're told that the probability that S is on BC, this red area here, is the ratio of the length of BC. That would be our favorable outcomes to the length of the whole thing, and that would be all the possible outcomes. So we would write this, the probability that when I pick that point that it'll be on BC is the length of BC divided by the length of AD. Alrighty, so remember, when you write your lengths, we don't need our little line segments over the top of BC and AD because we are talking about length. Alright, well let's do an example using that definition. So I got segment ST here, and point K is chosen on ST at random. So what is the probability that K is going to be on QR? So I'll make QR red like it was on our previous example. All right, so I know that I have to divide the length of QR by the length of ST. So how do I do that? Well, the length of QR, remember we did this in the very beginning, is 5 minus 8, the endpoints, and of course it's the absolute value. Why do I have to use the absolute value? Because it has to be positive. And the length of ST is the absolute value of 2 minus 14. So the number of possible outcomes here, absolute value of negative 12. Favorable outcomes is the absolute value of negative 3. So the probability that when I randomly choose this point K, it's going to be on QR is 3 over 12 or 1/4. And if you like to think of your probabilities as a percentage, then hopefully we know that that's 25%. So I got a 25% chance there of that point being on QR. All right, let's do another. Find the probability that a point chosen at random on ST will be on QT. All right, well, I'm going to highlight my favorable outcome length right here. So the probability that this point K will be on QT is the length of QT. So what is that? It's 5 minus 14 over the length of ST, 2 minus 14. So that's going to give me negative 9, absolute value of negative 9 divided by the absolute value of negative 12, which turns out to be 9/12, which if I simplify that is 3/4 or 75%. I got a 75% chance or 3 out of 4 chance of picking that segment randomly and having it be on QT. Okay, what we'll do most of in this unit though is, in this little section that is we'll talk about area because that's what our whole unit of study has been on. So when we talk about area, we're going to do pretty much the same thing. So I got this region here, I got this region R, and I want to know if I randomly choose a point S, what is the probability that it will be in this region N? So once again, I'm going to take the area of region N and I'm going to divide it by the area of region R, because region R is the total and region N is the favorable. Favorable always on top, total always on bottom. If you put the smaller one on bottom, what's going to happen? You're going to get a probability greater than 1, greater than 100%. Not possible. So guys, if you're ever working a problem and you find a probability and it's greater than 1, you know you got it wrong. You cannot have a probability greater than 1. Okay, so we're just going to do 2 or 3 little problems here to make sure we got this. So what do we have here? We got a circle inscribed in a square. A point in the square is chosen at random. What is the probability that the chosen point lies in the shaded region? So we're looking for probability that our point is going to be in the shaded region. So what's that going to be? So the favorable is the shaded. So we need the probability that it's in the shaded region divided by, I mean, not P. I want to call it, so I need the area. I need the area of the shaded region divided by the area of the whole thing, the total area. So favorable outcomes divided by total possible outcomes. So let's start with the total. Let's start with the total area. That's easy enough, right? I got a square, so I know that every side measure is 6. So the total area is going to be 6 squared, which is 36 square centimeters. All right, now we got to get the area of the shaded region. So how are we going to do that? It looks to me like we got to find the area of the circle and then do what? Subtract it from the area of the square, right? So let's get the area of the circle. So I know the area is pi r squared, and I know my radius. If the whole diameter, the diameter of the circle is the side length of the square, then I know my radius is 3. And I know the area is going to be 9 pi. 3 squared times pi, right? Okay, so now we got to subtract this area of the circle from the area of the square to get the shaded region. So the area of the shaded region equals area of square minus area of the circle, and that is 36 minus 9 pi. So our probability here is going to be 36 minus 9 pi divided by the total area, which is 36. That looks like something I need to simplify, doesn't it? So what can I do? I can factor a 9 out of my numerator. That's going to give me 4 minus pi divided by 36. Got to come down here and write my final answer. So the probability is going to be, let's see, 9 will go into that 1, 9 will go into that 4. So finally, the probability that we're going to randomly pick a point and it's going to be in the shaded region is 4 minus pi over 4. And that's it right there. And of course, there are no units on probability. I can't really change that into a percentage. I could if I wanted to estimate pi here, but I don't want to do that. I want to leave it just like it is. Okay, let's do another one. Suppose we have a target. A dart lands randomly on the target. What is the probability that the dart is going to land in the shaded region? So the probability, once again, that we're going to be in the shaded region is the area of the shaded region divided by the area of the total, the whole thing. So let's find the total area first. I always find the total first because that's generally the easiest thing to do. So the total area, let's see, my large circle is 8. No, wait a minute. This is 8 is just this little segment right there. So I need the radius of the largest circle. So that's going to be, this little part here is 2. This part here is 4. So I got 6 plus 8. So it looks like the radius of my large circle is, I'm going to write this down here. Radius of the large circle, 8 plus 4 plus 2, 14. 14, let's see, we don't have units, so that's what we got, 14. Okay, so the total area is pi times 14 squared. So that's going to be 196 pi. All right, so there's my total area. I'm going to go ahead and put that up here. And how am I going to find my shaded area? Okay, what I think I got to do here, guys, is I got to find the area of this circle here, the medium-sized circle, and then what have I got to do? I got to subtract out the area of the little small circle, right? That's how I'm going to find this shaded area. So let's find the area of the medium-sized circle. What's the radius of the medium circle? It looks like it's 4 plus 2, right? This little section right here plus the 2, so that's going to give me 6. So pi times 6 squared is going to be 36 pi. That's if I had the whole circle there, but like we said, so I'm going to put r medium equals 6, and the radius of the little tiny circle in the middle is 2. So now we're going to find that. The area of the small circle, the little one, is pi times 2 squared, which is 4 pi. So now I can finally find the shaded area. So the area of the shaded region is medium circle minus the small circle, which is 36 pi minus 4 pi, which is 32 pi. So that's what's going to have to go on the top, right? 32 pi. So the probability, I got to simplify this fraction here, guys, right? I know the pi's are going to cancel. No pi's. They're going bye-bye. So what I got to simplify is 32 over 196. And I think the largest number that will go into both of these is, let's see, 4. If I divide 4 into 32, I get 8. If I divide 4 into 196, I get 49. So there's my probability right there. I'll leave it in red. So the P that I'm going to randomly pick a point there, and it's going to be in the shaded region, is 8/49. And if you wanted to, excuse me, if you wanted to estimate what that percentage is, then of course we're just going to divide 49 into 8. I'll tell you what that is. And that is approximately 16%. Got a 16% chance of randomly throwing a dart and getting it in that shaded region there. All right, one more. Okay, guys, now this would be a good time for you to pause this video and try to do this one on your own, and then you can come back and see how you did. Choosing a point at random. What is the probability? All right, probability shaded. Once again, that's going to be the area of the shaded divided by the total area, because I could pick a point at random. It could be anywhere in that circle. So what do we got to do? Let's find our total area first. I always like to do that. Pi r squared, which is, let's see, our radius is 3 inches, so that's going to be 9 pi. There's our total area. We got an area of a sector here. So let's see, the area of the shaded region. So I know I got 83/60 of this whole circle. So there's the area of my sector, right? 80 degrees divided by 360 degrees times the whole thing. So let's see, if I want to simplify this for sure before I start dividing. 10 goes into both of these, 80 and 360, so that would leave me with 8/36. And then I can divide this 9 here. 9 goes into 9 1, 9 goes into 36 4 times. So before I do much other simplifying, let me come on over here and see what I got. I got 8/4 times pi, which is 2 pi. All right, so there's my shaded area. So I got 8 pi divided by the total area, which is 9 pi. This doesn't look quite right. That looks a little too large, right? If I simplify these, that leaves me with 8/9, which is almost my whole circle. So I have done something wrong here. I'm going to take a pause and I'll come back and fix it. Hang on. Okay, I see what I did wrong. This 8 pi right here. This 8 pi is supposed to be 2 pi. I don't know why in the world I wrote 8 pi, but anyway, that's what I did, so that's what I got to fix. The shaded area is 2 pi, so my probability is 2 pi over 9 pi. That looks a lot better. So my probability that I would randomly pick a point in that shaded area is 2/9. And if you're a percentage person, we'll say that that's approximately 2 divided by 9. That's approximately 22%. All right, so that's it, guys. Write a summary, practice.